So this is the third lecture on the RSA cryptosystem. And in this lecture, I'm going to describe the main attacks against RSA signatures and how to have provable security for RSA signatures. So let me first recall the textbook RSA signature scheme that we have already seen before. So for the key generation, we generate the public RSA modulus n equals p times q, where p and q are two large primes. The public exponent is e and the private exponent is d, such that d times e is equal to 1 modulo phi of n. And then to sign a message m with textbook RSA, the signer is going to compute s equals m to d modulo n. So we see that only the signer can sign the message. And then to verify the signature, we check that m is equal to s to e modulo n. So this works because raising to d and raising to e are inverse operations. And so we see that anybody can verify the signature. So of course, as we have seen before, textbook RSA signature is not secure because we can describe two attacks. So for example, the existential forgery, we can generate some arbitrary R, and if we raise R to E, we get a message M, which is arbitrary also. And we see here that R is a valid signature of M because the verification equality holds. So this means that we can construct a pair of message and signature without knowing the private key, only from the public key. So this is a first attack, and another attack is a chosen message attack. We see that when we multiply the signature of M1, M1 to D, by the signature of M2, M2 to D, we obtain the signature of M1 times M2, M1 times M2 to D. So this shows that if we are given two signatures of M1 and M2, we can construct a third signature simply by multiplication modulo n, so without knowing the private key. And this is a bad property, of course, because this means that we can really forge signatures. We can obtain signatures on messages that the legitimate signer has never signed before. And the usual countermeasure against these attacks is to not sign M directly. First, we encapsulate M using the message M using an encoding function mu of M. And we only raise mu of M to the power of D modulo n instead of M directly. And this gives us the signature. So of course, the main question is how do we choose this encoding function mu of M? So there are basically two kinds of encoding functions mu of M. So there are the old ad hoc encodings, the first generation of encodings, which can be found on various standards. So for example, PKCS1 version 1.5, the ISO 9796-1 and ISO 9796-2. So these encodings were designed to prevent specific attacks, but as we will see, they can exhibit some weaknesses and some pretty severe weaknesses. And then we have the second class of encoding functions for which we can prove that the signature scheme is secure. So of course, this is much better. And so in this lecture, I'm going to describe the RSA full domain hash signature scheme and the RSA PSS scheme with the corresponding encoding functions. And then for these signature schemes, we can prove that they achieve a well-defined definition of security under well-defined assumptions. But this is what I'm going to explain. So here are some examples of ad hoc encoding functions, so without security proof. So the signature is always mu of M to the power of D modulo n. And so there is the old ISO 96-1 standard, where to sign a message M, we split it in a sequence of 4-bit nibbles, and then we apply a lookup table S to each nibble independently, and eventually mu of M is the concatenation of these nibbles and the lookup tables. So this means that when we verify the signature, since the message M is embedded inside mu of M, we can recover the message when verifying the signature. We don't have to transmit the message separately. This is also the case in the ISO 9796-2 standards, where the mu of m has the same size as the modulus. And so we have, it starts with a constant, 6a, then some part of the message can be embedded inside the mu of m. Then there is the hash of the full message m, and then some constants. So again, this means that when we verify the signature, so we recover some part of the message, this m1. And there is also the PKCS1 version 1.5 standard, in which is where mu of m is also full size. And so it starts with a constant, then some constant specific to the hash function being used. So for example, SHA-1, and the hash function is the SHA-1 hash function, which has 160 bits. But the main problem with these ad hoc encoding functions is that we can have some attacks. So the main attack is the decimal disco attack, which was described at Crypto 85. So I'm going to describe this attack, and then I'm going to explain why it can be applied to the ISO standards. So the attack works as follows. So the attack works. The basic decimal disco attack works only if we assume that the encoding message mu of m is relatively short. That is much shorter than the RSA modulus. So the attack works as follows. We fix some bound big B, and we consider all the primes smaller than this bound B. So we have L primes, P1 to PL, which are the primes smaller than B. And then our goal is to generate messages, MI, such that the encoding of MI is B smooth. So this means that all the prime factors of mu of MI are smaller than this bound B. So they can be, this mu of MI can be factored into the product of primes P1 to PL with the exponents VI1 to VIL. So the goal is to find L plus 1 such messages MI, such that this mu of MI is smooth. So can be factored into the product of small primes. So that's why this mu of M must be relatively small, because otherwise, if mu of M is full size, the size of the RSA modulus, this happens with negligible probability. And then the second step is to obtain a linear dependence relation between the exponent vectors. So we write the vector for each mu of mi, we write the corresponding vector of exponents. So vi1 modulo e to vil modulo e. So we consider these exponents modulo e the public exponent only. And then we try to obtain a linear dependence between these vectors. So we express one vector as a linear combination of the others. And then this means that one of the mu of mi, so for example mu of m2, can be expressed as a multiplicative combination of the mu of mi. So that is the linear relation on the exponents gives us a multiplicative relation on the mu of mi's. And then the attack, this means that we can have a forgery, because once we have this multiplicative relation, we see that the signature of the mu of m2, so mu of m2 to the power of d, is the product, a multiplicative product of the signatures of the mu of mi. So the forger is going to ask the signature of the messages mi, so he will obtain mu of mi to d, and then he can compute a new signature for a message m2 that has not been signed by the legitimate signer, and using only public information. So in that case, this is a forgery. So I'm going to explain these steps in more details. So assume that we have found these mu of mi's, which are a list of mu of mi's, which are B smooth. So that can be expressed as, that can be factored into the product of small primes. So we have obtained two such messages. And then, as I said before, we are going to associate to each mu of mi the corresponding vector of exponents modulo e. So we have this vector vi, which is vie modulo e to vil modulo e, which corresponds to the exponents in the prime factorization of mu of mi. And then, assuming that e is prime, then we know that the set of L-dimensional vectors, so the dimension is L because we have L prime factors, we know that this set of L-dimensional vectors modulo E forms a linear space of dimension L. So this means that if we have more than L vectors, so if tau is greater than L plus 1, we know that for sure we can express one vector, so for example v tau, as a linear combination of the others, modulo E. And this can be done easily using Gaussian elimination. So if we write this in terms of vector, we have that the vector v tau is a linear combination of the vectors vi. So the sum for I equals 1 to tau minus 1 of beta I vi. And since we are working modulo E, we get plus gamma, a vector gamma, times E, where gamma is a vector of integers. So we can rewrite this linear relation on the exponents. So we get that the exponents v to j is equal to gamma j, so the integer gamma j, which comes from the vector gamma, times E, plus the sum for I equal 1 to tau minus 1 of beta I times vij. So here we have written each of the j components. And then it's easy to derive from this linear relation a multiplicative relation on the encoding mu of mi's, because mu of m tau by definition is the product of the pj to v tau j. So this is by definition the factorization of mu of m tau, which is assumed to be smooth. And so we replace the v tau j by the linear relation. So this gives the product of pj to gamma g E plus the sum of beta I vij. And then this we can replace, so the sum is on the exponent, so which means that we obtain the product for I equals 1 to tau minus 1 of pj vij times beta I. And then we can swap the two products. So we write the product over the messages mi first. So we have the product for I equals 1 to tau minus 1 of the product for g equals 1 to L of pj vij to beta I. And by definition, this product of the prime factors is exactly mu of mi. So eventually we obtain that mu of m tau is something to the power of the public exponent e times the product of the mu of mi to the power of the exponent beta I. And then so we can rewrite it like mu of m tau is equal to delta to the power of e, so where delta is a known integer, times the product for I equals 1 to tau minus 1 of mu of mi to the power of beta I. And now since we have this delta to the power of e, it's easy to derive the forgery. So because when we raise this previous equality to the power of d modulo n, we obtain that the signature of the message m tau, by definition it's mu of m tau to the power of d, it's equal to delta, because we have delta to e, so delta to e to times d is equal to delta, times the product for I equals 1 to tau minus 1 of mu of mi to d to beta I modulo n. And by definition, this is the product of the signatures sigma I to the power of beta I. So now we can express one signature as a multiplicative combination of the others, modulo n. So this means that we have our forgery. So we would like to compute the success probability of this attack and the complexity actually of this attack. But for this, we have to estimate the probability that an integer is smooth, that it can be factored into small primes only, because this is what is going to determine the complexity of our attack. So there is a theorem which says that if x is an integer, we define the function Lx of beta, which is exponential of beta times square root of log x log x. And then if we consider t an integer randomly distributed between 0 and x, then we know that for large x, the probability that all the prime factors of t are less than Lx of beta, so it is Lx beta smooth, this probability is Lx of minus 1 over 2 beta plus something negligible. So this theorem gives us an estimate of the probability that an integer is going to be smooth as a function of the parameter beta. So the parameter beta determines the bound on the prime factors that can appear in the factorization of t. So how do we apply this theorem? In our case, we let x be a bound on mu of m, our encoding function. So that's why mu of m should not be too large. And we define L as Lx of beta, be the number of primes. So here the bound on the value of the primes will not be too much different from L. And so we do this for some parameter beta. And then the theorem implies that the smoothness probability is Lx of minus 1 over 2 beta. So if we take a small beta, so a small value of L, so a small number of primes, then the smoothness probability, of course, is going to decrease. So if beta is small, then Lx of minus 1 over 2 beta is going to be very small. So as we will see, we will have to optimize the value of beta. If beta is too small, then we are never going to obtain any smooth integer. But if beta is too large, this means that we have to have a huge base of prime factors, and then our attack will not be efficient. So we are going to optimize the value of the parameter beta. So the complexity. I'm going to describe the asymptotic complexity analysis of the Desmet-Odisco attack. So as we have seen, the smoothness probability is Lx of minus 1 over 2 beta plus something negligible. So this means that to obtain a single smooth mu of mi, so a single message mi for which the encoding mu of mi is smooth, it's going to take Lx of 1 over 2 beta plus something negligible time. So this is the inverse of the previous probability. And we know that to obtain our linear relation, we need at least L plus 1 smooth encodings. So this means that the total running time will be the product of L, so which is Lx L plus 1, or L, which is Lx of beta, times this the complexity to generate a single smooth encoding. So it's Lx of 1 over 2 beta plus something negligible times Lx of beta. And this gives us Lx of 1 over 2 beta plus beta. So we want to minimize this complexity. So we want to minimize the constant 1 over 2 beta plus beta. And we see that the complexity is minimal when we take beta equals square root of 2 over 2. And then the asymptotic complexity is Lx of square root of 2 plus something negligible. So we see that the complexity is sub-exponential in the size of mu of m. And so it is sub-exponential in log x, where x is the bound on mu of m. So it means that it is sub-exponential in the size of mu of m. And so in practice, the attack is only practical when mu of m is relatively small, so less than 160 bits, which is roughly the upper bound. And now there are many applications of the Desmet-Odisco attack. So a first application was the cryptanalysis of the ISO 9796-1 standard and ISO 9796-2 signature standards. So it was an extension of the Desmet-Odisco attack, and the attack for ISO 9796-1 was very efficient. So the standard was withdrawn, and the ISO 9796-2 was amended by increasing the digest size, because the complexity of the attack depends on the size of the hash function, on the output size of the hash function that is used in the standard. So it was amended to make it at least 160 bits. And then there was again, 10 years later, a cryptanalysis of the ISO 9796-2 standard using an improved detection of smooth integers and using a very clever algorithm by Bernstein. And so the complexity is still sub-exponential, but much more efficient than the previous attack. And so it could work even against the amended ISO 9796-2. And following this attack, the standard was amended again in late 2010. So of course, this situation is not very satisfactory because we have many encodings which have been broken, and so what we would like is to have a guarantee of security. We like to know that for sure the encoding, the signature scheme based on RSA is never going to be broken. So the question is how can we justify security rigorously? And the approach is actually to prove that if an adversary can break the scheme or signature scheme, then we can use this adversary to solve some well-defined hard problems, such as, for example, factoring integers or inverting RSA. So the problem of inverting RSA is given a challenge y to compute y2d modulo n without knowing the private key, of course. And in that case, if we can prove this reduction, then in that case, this shows that the scheme is secure, assuming that the underlying problem is hard to solve. So this means that if we assume that inverting RSA is hard, then we can have a guarantee. We have a guarantee that our signature scheme is secure. But for this approach, of course, we must first specify what it means for a signature scheme to be secure. So what it means to break a scheme. A signature scheme. So for this, we need a security definition. So the standard security definition for signatures is the security definition of Goldwasser, Micali, and Rivest in 1988. And under this definition, it should be infeasible for an adversary to forge the signature of a message. So this means to produce a new signature for a message that has not been signed before, even if the attacker can obtain the signature of messages of his choice. So I will explain this notion in more details. And then, based on this security notion, we can try to have a security proof. We can try to prove the security of a scheme. And for this, we show that if we have an adversary who can break our signature scheme, who can forge signatures according to this security definition, then we can use this adversary to solve a difficult problem such as inverting RSA. And so conversely, this means that if we assume that inverting RSA is hard, then there can be no such adversary, and so our signature scheme is secure. So here below are some examples of signature scheme for RSA for which we can have such security proof. So these are the full domain scheme that I'm going to describe, and the probabilistic signature scheme PSS, which is probably the most widely used signature scheme based on RSA. So let me explain the security model in more details. So the security model is as follows. So initially, we have the reduction, so our algorithm that receives as input the challenge of the problem, of the RSA problem. So it receives as input the modulus n, the public exponent e, and the challenge y. And the goal of the reduction is to compute y2d modulo n. So the reduction cannot do it by itself because this is presumably a hard problem, but the reduction is going to use the forger to solve this hard problem. And then if we assume that solving this problem is hard, this means that such forger does not exist, and this means that our signature scheme is secure. So as a first step, the reduction is going to send the public key n and e to the forger. Then the forger can make signature queries, as many signature queries as he wants. So this means that the forger submits a message to the reduction, a message mi, and then the reduction must output the corresponding signature of the message mi. And then eventually, the forger stops making signature queries, and he outputs a forgery. So that is a pair of message M prime and sigma prime, and where sigma prime is the signature of M prime, and M prime, of course, has never been requested before. It's a new message. And eventually, the reduction is going to use this pair M prime sigma prime to solve the RSA challenge and to compute, hopefully, Y2D modulo n. So let me describe the full domain hash signature scheme, which is actually the simplest signature scheme based on RSA. So it was designed in 1993 by Bellard and Rogaway. So we start from the message M, we hash it, so we get h of M and the hash of M, and the signature is simply the hash of M to the power of D modulo n. And it's called full domain hash because the hash function h of M has the same output size as the modulus. So if the modulus has 1024 bits, then the hash function must have 1024 bits. And as we will see, we can show that for full domain hash is probably secure, is a probably secure signature scheme in the random oracle model, and assuming that inverting RSA is hard. So this means that if we assume that inverting RSA is a hard problem, then there is no efficient attack against full domain hash. So in the random oracle model, this means that we replace the hash function, we view the hash function as a random oracle. And this random oracle is going to output a random value for each new query. So what does it mean? A proof in the random oracle model means that the adversary is not autonomous with respect to the hash function. He cannot compute the hash function by himself. He must query the random oracle. So every time he wants to compute the hash of a function, the hash of a message, then he cannot do it by himself. He must query the random oracle, and the random oracle outputs a new value, which is randomly distributed. So here, for simplicity, we are going to assume that the hash value is uniformly distributed modulo n. But we could have actually a uniformly distributed string which will have the same length as, or approximately the same length as the modulus n. So we see that this is actually an idealized model of computation, because in practice, the hash function that is that is used for the scheme is well defined. For example, it can be based on SHA-1, and for SHA-1, of course, the attacker can compute the hash of any message of its choice. It doesn't have to query a random oracle. So this is an idealized model of computation, and even if we have a proof in the random oracle model, this does not imply that the scheme will be secure when we use a concrete hash function such as SHA-1. Still, it is a good guarantee, and the advantage is that the proofs are relatively simple to understand. So we have to modify our security model a little bit to take into account these hash queries. So as previously, the forger or the attacker receives the public key as input, and then he can make hash queries, because he cannot compute the hash of a message by himself. He's going to make hash queries, and when we use the forger, we must answer these hash queries. And as explained previously, the forger can still make signature queries for messages MI, and then he receives the signature, and eventually the attacker outputs the forgery, so a new signature sigma prime for a new message M prime that has not been queried before. So the proof of security is going to work as follows. We assume that we have a forger on the left, and what is this forger? The forger is an algorithm that receives as input the public key for the signature scheme, so the modulus n and the public exponent e, and the forger is going to make at most QH hash queries, so QH is a parameter, and at most QSIG signature queries, where QSIG is also a parameter. And so eventually is going to output a forgery, M prime and sigma prime, where sigma prime is a new signature. And then we are going to use this forger to solve or RSA challenge. So we are given as input, initially we are going given as input N, E, and Y, and our goal is to use the forger to compute Y to D modulo N. So we are going to use the forgery that is being returned by the adversary to compute this Y to D modulo N without knowing D, of course. And so this means that using the forger, we can solve this RSA challenge. And conversely, if we assume that solving an RSA challenge is a hard problem, that there is no efficient algorithm that can solve this problem, this means that producing a forgery must be hard, and so there are no attacks against full domain hash. So I'm going to describe in more details the security proof for the specific scheme full domain hash. So initially, our reduction receives as input the challenge, N, E, and Y, and our goal eventually is to compute Y to D modulo N after interacting with the forger. So we are going to use, our goal is to use the forger in a clever way in order to solve this RSA challenge. So for this, we proceed as follows. First, we are going to generate a random index J between 1 and QH plus Q6 plus 1. So because we know that the maximum number of messages that can appear when interacting with the forger, this total number of messages is upper bounded by QH plus Q6 plus 1, because there are QH hash queries, Q6 signature queries, and eventually the forgery. So there are at most QH plus Q6 plus 1 possible messages. And so we select a random index among all these possible messages. And then the forger is going to make hash queries. So for this, when we receive a hash query from the forger, we must answer it, of course, and we distinguish two cases. If the index of the message mi that we receive, if the index is not equal to j, to this specific index j that we have randomly selected initially, we say that the hash of mi is equal to ri to e modulo n. So we see that this is a good simulation of the random record because we generate a random ri and we raise ri to the power of e modulo n. So this remains, since RSA is a permutation, this remains uniformly distributed modulo n. So h of mi is uniformly distributed and independently for each new message mi. And if I is equal to j, then we say that the hash of mj is equal to y modulo n. So here we can do this. We can actually determine the output of the hash function because we are working in the random oracle model. In the random oracle model, here we simulate the random oracle, and so we can generate the hash value as we want, as long as it is uniformly distributed. So this is for the hash queries, and then the forger is going to make signature queries. And then, again, we distinguish two cases. If he makes a signature query for a message mi, where I, the index of the message mi, is not equal to the specific index j, then we can compute the signature easily because the hash of mi is equal to ri to e, and so this means that the signature sigma I is simply equal to ri, which is ri to e to d. So in that case, we know the signature is ri, and we can output this signature. But if we are unlucky and the attacker makes a signature query for the message mj for the index j, then we cannot answer the signature query, and in that case we must abort. And so eventually the forger is going to output a forgery for message m prime and the signature sigma prime. And then if we are lucky, then the message m prime will be equal to mj. So in that case, we have guessed so the goal of the index j is actually to guess for which message the forgery will occur. So if we have guessed correctly, if we are lucky, then this means that the hash of the message mj is equal to y, and so this means that the signature sigma prime is equal to y to d modulo n. So here we have obtained that what we want. We have obtained Y to D thanks to the forgery of the forger. And so this means that we solve the RSA challenge. Eventually, we can output Y to D modulo n. So let me summarize this again. So we denote by QH the maximum number of hash queries and QSIG the maximum number of signature queries by the forger. So first, as I said, we select a random index J among all possible indices of messages. So between 1 and QH plus QSIG plus 1. And then when we receive a hash query for the message number I, if I is different from this specific index J, we let h of mi, we program the hash function to be ri to e modulo n for some random ri, so it is uniformly distributed as required. And if I is equal to j, then we say that the hash value is equal to mj, which is y, where y is the challenge, and actually we assume that y is uniformly distributed modulo n by definition. And then when we must answer a signature query for a message mi, we distinguish two cases. If I is not equal to j, then in that case the hash of mi is equal to ri to e, and therefore the signature sigma I is the hash of mi to the power of d, which is equal to ri modulo n. So we can output ri, we know the signature, and we output ri. But otherwise, if I is equal to j, so if we have received a signature query for mj, then we don't know the signature, so we must abort. So we see that we can answer all the signature queries except for the message mj. And then eventually the forger is going to output a forgery. And so for the pair m prime sigma prime. And so we can assume actually that the adversary has already made the hash query for the message m prime. So m prime is equal to some mi for some index I. Otherwise, we could simulate this hash query. And then, if we are lucky, if I is equal to j, so the forgery that is for the message mi that is produced by the adversary is for the index j, for the jth message, then we obtain that the signature, the forgery that has been produced by the attacker is by definition equal to the hash of mj to d, and this is exactly y to d because the hash of mj is equal to y. And so this means that we are successful. We have computed y to d, and so we can return sigma prime as the solution of the RSA challenge. So we have correctly solved the RSA challenge. So we see that our reduction, our algorithm succeeds if, when we are lucky, when we have correctly guessed the index of the forgery, when I is equal to j. And since j was selected at random, between 1 and QH plus QSIG plus 1, this means that we succeed with probability 1 over QH plus QSIG plus 1. So we can now compute the success probability of our reduction. So we obtain that from a forger that breaks full domain hash with probability epsilon in time t, we can invert RSA using our algorithm with probability epsilon prime, which is epsilon over the previous success probability. So epsilon over QH plus QSIG plus 1, because the two probabilities are independent, because we are selecting the index j independently at random. And the running time, the total running time of reduction is very close to t, because we don't have much computation beyond running the forger full domain hash. And so conversely, this means that if we assume that it is impossible to invert RSA with probability greater than epsilon prime in time t prime, then it is impossible to break full domain hash. So full domain hash is secure against forgery. So it is impossible to break full domain hash with probability greater than epsilon equals QH plus QSIG plus 1. So this penalty factor times epsilon prime. And the running time in running time t close to t prime. So the running time of the forger is close to the running time t prime, which is the upper bound to invert RSA. So this means that if we assume that epsilon prime is very small, then for reasonable values of QH plus QSIG plus 1, then the probability of breaking full domain hash in a limited amount of time, t, this probability will also be small. And so this provides the security guarantee that we are looking for. The full domain hash signature scheme is secure, assuming that inverting RSA is hard. And now there is a technique to improve the security bound, because we would like to decrease this penalty factor between inverting RSA and breaking full domain hash. And so for this, we can use the following trick. So instead of letting h of mi equals ri to e modulo n for all indices I different from j, and letting h of mj equals to y, we are going to use y more often. So the challenge y, which is in the original security proof, it is embedded inside the hash function only once. We are going to use it more often. So for this, it works as follows. So when we receive a message mi, hash query mi, for mi, we let h of mi equals ri to e modulo n, so as previously, but only with priority alpha. And otherwise, so with priority 1 minus alpha, we let h of mi equals ri to e times y. So we use our challenge y, and we randomize this challenge because the hash values must be uniformly distributed. So we must randomize the hash values. And now we see that there are two kinds of messages, mi. So the first, in the first class, the hash of mi is equal to ri to e modulo n. So we know the corresponding signature, which is ri. So we are able to answer the signature query from the adversary, if the adversary queries the signature of mi, because so the signature sigma I is h of mi to d, which is ri modulo n. And in the second, there is the second class of message, which is when h of mi is equal to ri to e times y. So when we use the challenge y, in that case, we don't know the corresponding signature. But if the adversary makes a forgery for this specific message mi, we can use the forgery as previously to compute y to d using a similar computation. Because if h of mi is equal to y times ri to e modulo n, then the signature by definition is h of mi to d, which is equal to y to d times ri. So which means that we can divide by ri, and we obtain y to d modulo n, the solution of the challenge. And now we see that we must optimize for the probability alpha. If alpha is too high, very close to 1, then in that case we can answer all the signature queries with good probability. But when we receive a forgery, most of the time is going to be useless because we already know the signature. When we receive a forgery for a message mi for which h of mi is equal to ri to e, then this forgery is basically useless for us because we already know the signature, and the forgery gives us no information. So, but if alpha is too small, then in that case, the forgery is going to be useful with good probability, but sometimes we will not be able to answer the signature queries, because when h of mi is equal to ri to e times y, we don't know the corresponding signature. And so if there is a signature query from the adversary for this specific message, then we must abort, and we have failed. So we must optimize for alpha, but it is easy to optimize by computing alpha by computing the corresponding success probability for reduction. So we see that the probability that all signature queries are answered is actually alpha to the power of qsig, because each individual signature query is answered with probability alpha, and all these events are independent. So if there are at most qsig signature queries, then we know that we can answer all the signature queries with probability at least alpha to qsig. And now, what is the probability that the forgery mi sigma prime is useful? It is useful is for the message mi, the hash of mi is equal to ri to e times y modulo n. And so this happens with probability 1 minus alpha by definition. So globally, the success probability is the product, so alpha to qsig times 1 minus alpha. And so we simply have to maximize this function, so we compute the derivative, and we see that the maximum is there is an optimal alpha, which is 1 minus 1 over qsig plus 1. And then asymptotically, we obtain that for large values of qsig, the optimal is roughly 1 over exponential of 1 times qsig. So it's roughly 1 over some constant times qsig. So as previously, we obtained that if we have a forger that breaks full domain hash with probability epsilon in time t, then we can use this forger to invert RSA with probability epsilon prime equals epsilon over 4 times qsig. Here I have replaced the exponential 1 by 4. And so, and conversely, if we assume that it is impossible to invert RSA with probability greater than epsilon prime, then it is impossible to break full domain hash in roughly the same amount of time, and it is impossible to break full domain hash with probability greater than epsilon equals 4 times qsig times epsilon prime. So we still have a penalty factor, which this time the penalty factor is 4 times qsig instead of qh plus qsig plus 1. And now we can assume that actually qh is much larger than qsig, because we can assume that the attacker is going to compute a huge number of hash queries. So we can take, for example, qh equals 260, but the number of signature queries can be lower. We can assume that it is lower. So we can take qsig equals 2 to 30. And so in that case, the penalty factor is 2 to 32. And so we obtain that epsilon equals 2 to 32 times epsilon prime, instead of 2 to 60 times epsilon prime. So this means that we have improved the security level. We have shown that actually full domain hash is more secure than initially proven in the original security proof. So we obtain a better level of security for a given modulus size k. So this means that for the same level of security, we can use a smaller RSA modulus, and so this we can say that this improves the level of efficiency. So now I'm going to say a few words about the PSS signature scheme, which is the most widely used signature scheme based on RSA. So it was designed also by Bellard and Rogaway at Eurocrypt 96. So it appears in many standards. So there are two variants, PSS and PSSR with message recovery. So this means that we recover the message when we verify the signature, so we don't have to transmit the message separately. And so as previously, as full domain hash, it is probably secure against Trojan message attacks in the random oracle model. So now let me describe PSS with message recovery. So the encoding function of the message M is omega and S. And this encoding is actually probabilistic, so we are going to use some randomness R. So when we want to sign a message M, we generate some randomness R, and then we concatenate M and R, and we use the hash function H, which is publicly known, which is part of the standard, to obtain omega, and we hash omega with the hash function G, and we XOR the result with M and R to obtain the second part of the encoding S. And then, so this gives us the encoding, omega and S, and then we raise this encoding to the power of D to obtain the signature sigma. And then to verify a signature sigma using the public key, we first raise sigma to the power of E, of course, to recover the encoding omega and S. And then we hash, once we know omega, we hash omega with the hash function G, and we XOR it with S, and then we recover M, the message M, and the randomness R. And then eventually we check that when we hash M and R, we obtain omega. And in that case, we can say that the signature is correct. And so the advantage of PSS compared to full domain hash is that we have a tight security proof. The probability of breaking PSS is roughly the same as the probability of inverting RSA. So there is no security loss. So we can say that PSS is actually more secure than full domain hash. So now I'm going to say a few words also on implementation attacks, which are very important in practice, because in practice, when we implement a cryptographic algorithm, the implementation can reveal more information than the input-output behavior. So we can distinguish two classes of attacks. There are the passive attacks, in which, and so for example, the timing attacks, in which the attacker is going to measure the execution time, and this can reveal information on the underlying secrets. And the very powerful attack is the power attacks, which measures the power consumption of the device. So for example, a smart card. And from this power consumption, we can recover the secrets when there are no countermeasures. So these are the passive attacks, which do not modify the microprocessor, or which do not affect the computation. And there are the active attacks, which are going to modify the computation. So for example, the fault attacks, the goal is to induce a fault during the computation. So the result will be incorrect, but from this incorrect result, we can compute the secrets. So let me describe the classical fault attack against RSA CRT. So such fault attack can be obtained by, for example, by modifying the input voltage of the device, and then the result, some result is going to be faulty, or we can use a laser to illuminate the processor, and this can generate a faulty computation. So the attack applies against RSA with CRT. So in that case, to compute the signature S equals M2D modulo N. So here I describe the attack for signatures, but the attack also applies for RSA decryption. So to compute the signature S equals M2D modulo N, we first work modulo P. So we compute M to the power of dP modulo P, where dP is the exponent when working modulo P. So dP is d modulo P minus 1. And we compute the part modulo Q. So SQ is M to dQ modulo Q. So where dQ is d modulo Q minus 1. And then we know that we can recombine SP and SQ to obtain, using the Chinese remainder theorem, to obtain the signature S equals M2D modulo N. So the fault attack is quite simple. We can induce some fault during the computation of, for example, of SP. So in that case, SP will be incorrect. SP should be equal to M to dP, but using a fault, so for example, by modifying the input voltage, this SP value will become incorrect. So this implies that eventually the signature that we are going to compute will be incorrect. It means that S2E will not be equal to M modulo N. But still, if we assume that the result is still correct, there was no fault, no error during the computation modulo Q, we still have S to the power of phi, which is equal to M modulo Q. So here we have that S2E is not equal to M modulo N, but it is equal to M modulo Q. So this means that Q divides S2E minus M, but P does not divide S2E modulo M. And so this means that when we take the GCD, we have that Q is a common factor between N and S2E minus M modulo N, and so we can recover this prime factor Q. And so we completely break the signature scheme.